Now we want to look at some more complex divisions. So this time, instead of 1 over over a function, we want to have a situation where we've got a function divided by another function. To do this, what we're going to try and do is look at multiplying the two functions, the multiplication of the two functions first. So in that case, what we've got is to draw it up. We want to draw the x in. We take x cubed minus times x minus say x minus 3 times x minus 2 times x plus 1 first, and then be able to solve do a division involving these ones. So again, that's from our extension 1. We know that's how that would graph up. We goes through minus 1, 2, and 3. From here, we know it tends to negative infinity, and it tends to positive infinity. It'll go through at 6. Because when x is equal to 0, it goes through 6 there. So if using that idea to graph x minus 3 over x minus 2 times x plus 1, well, how does that help us? Well, again, from what we've just had, we can get our signs from the multiplication, because it doesn't matter whether multiplying or dividing, the signs will stay the same. We get our asymptotes from these two, so we know where that went through the x-axis. So at minus 1 and positive 2, we've got them going through the x-axis. We know it stays at x is equal to 3, that it goes through the x-axis in this case. We can also find where it goes through the y-axis. When x is equal to 0, would give us minus 3 over minus 2 times minus 1, which is positive 1.5. So that's why that's where it's going through. So we're able to get some critical values there. So our asymptotes going through at 3, going through there at 1.5. Notice the signs will stay the same. So between the asymptotes there, it was positive before, so it stays positive. On the left side of x is equal to 1 minus 1, it was negative, so it stays negative. Between 2 and 3, it was negative, so it will be staying negative, and after 3, it was positive, so it remains positive. Again, as it says down here, if you read this part, as it tends to positive, or the function tends to there before to positive or negative infinity, the curve reaches an asymptote of the x-axis there. So it gets there, and as it approaches the asymptotes, it approaches positive or negative infinity. There is a turning point at x is equal to 1, and you can find that after differentiating. So you'd have to differentiate that to do that. Now that's not pleasant to do that. So I haven't done it here, but that's how you would get that turning point at x is equal to 1 and doing it there. The same thing would happen here. There must be a turning point somewhere here, because it comes up and goes up and then starts to tend towards 0. So there must be a turning point as well there, which you'd find with the derivative of that function. So if you're asked to do one like this, then you might be asked to find the derivative at some stage as well. So that's, again, there's the sorts of things we've got to look at. Using x minus 1, x minus 4, x squared minus 4 as a guide. Again, what does 1 on the function there look like? Well, again, we've got our asymptotes, we've got our signs of the function, we've got where it approaches the asymptotes. Now it's going to approach positive or negative infinity, and as it approaches infinity, it's going to approach 0 at those particular values. You've got the turning points as well, be able to match them up. So a bit more complex example, x minus 2 over x squared, x minus 1 times x plus 2. So what does this one look like? Well, again, we're relating it back to this one, x minus 1, x minus 2, x plus 2. So we've done 1 over the function there, and now it's using that curve again, except the point this time where x minus 2 is not in a denominator, it's being divided by the other 2. So again, we're able to see that it's going to go through the function at 2 there, so we're going to have that matching up. We get the other 2 points which are in the denominator as our asymptotes, so we're able to get our way our curve looks. We're able to find by putting x is equal to 0 that it goes where it goes through, and that's the function's going to go through at positive 1. So when we put x is equal to 0 in there, so we can know where our function here is tending, so we know where the curve is going to tend as well in terms of the asymptotes. So we're able to use the blue curve to help draw up our new curve there. This time x plus 2 is in the numerator, and the other two are in the denominator. So we were able to see that it was going to cross at x minus 2 there. And again, it doesn't really show up, but it comes down and crosses the curve, but then it's going to tend to 0, so it must turn somewhere there. So you can see it's turning there, so it must turn at this point here as well. We've got our asymptotes here, so, and we can see where it tends to infinity here, it's tending to 0 as well there. This time the x minus 1, x plus 2 is up on top, so, and only the x minus 2 is in the denominator. So we've only got the one asymptote, and so it's going to cross the curve at minus 2 and at positive 1. So you can see where it's crossing the curve there. Again, it's tending to infinity there. It goes off. Because it's x squared on the x there, it's not going to tend to go necessarily that far because it's more dominant on top. So it's going to move upwards there. It's not going to tend towards in 0 as such. So it's a little bit different in that case because it's a greater function on top there. Now let's have a look at one where we have the functions in the numerator and the denominator at the same degree. Now hopefully remember what degree means. Okay, when we have that situation, we're going to get a horizontal asymptote, and we can show why we're going to get a horizontal asymptote. Let's take x minus 1 over x plus 1, and we're going to have the situation where we can do the division and break it up. Either do the polynomial division, like you can do it that way, or you can decompose it and say, well, if I'm going to get an x plus 1 there, that would be a minus 2 over x plus 1 to give us x minus 1 over x plus 1, where that would become 1. And as this part now will become close to 0, as x approaches infinity, that part's going to become 0. Then we'll approach y is equal to 1. Now, when we do that, that means we're going to get a horizontal asymptote. So if we're looking at something like that, what's our function going to look like? So again, we've got the x, we've got basically 1 minus 2 on x plus 1. Now we know how to draw up 2 plus x minus 1. Then we know we can draw up minus 2 on x plus 1, and then we shift it up 1 unit. So it's approaching the asymptote of 1 there. 1x on x plus 1, again, I like to decompose. I think it's a little bit easier than trying to do polynomial division. We get x plus 1 on x plus 1 minus 1 on x plus 1. So again, if we can draw up minus 1 on x plus 1, which we've done before, just shifting it up 1 unit. So it goes up, and we've got that horizontal asymptote that's approaching in there in the blue one. The red one's minus 1 on x plus 1, so you can see how it's being shifted up. X minus 3 on x plus 2, again, decompose it to get 1 minus 5 on x plus 2. So, and we're able to get that as we are able to draw up minus 5 on x plus 2 and shift it up 1 unit. X squared on x squared minus 1, again, same degree, but what does this approach? Now, we get the x squared minus 1 on x squared minus 1 plus 1 on x squared minus 1. So we get 1 plus 1 on x squared minus 1. So again, draw 1 on x squared minus 1 using our techniques that we did before. Shift the whole thing up 1 unit. Okay. And again, we can see the same degree. X minus 1, x plus 1, x minus 2, x plus 2. So we can see where we're going to get our asymptotes at minus 2 and 2. We're going to draw it up as if it was, and we're going to have the horizontal asymptote at 1, because again, because it's the same degree, it's going to have a horizontal asymptote of 1, and there's no number out the front to have a multiplication factor of that, so that's where it's going to have our horizontal asymptote, and that's where it's going to affect, because as the numbers get larger there, basically they're going to tend to infinity on infinity, which is going to approach positive 1 as such there. Same idea with this one. We get our we get our vertical asymptotes, minus 6 and minus 1, and we're able to note again, if we went through and multiplied this out, what would we get? and be able to get our correct sign. So we're able to get the signs there. We know it's going to go between -2 and -3. It's going to give us 0, so it's a little bit harder to see. But there we've got our values. I think I've got the right ones there. It's going to be 0. So it's just above the curve there, because when it's between -2 and -3, it's going to make it positive, and otherwise it's going to be negative there. So that's why you're able to draw. If you draw up the 4 there, we're able to get our asymptotes and where it crosses the axis. My scale's a little bit large here to give me that effect as such, but that's what should have effect in. So we've got to look at that in that respect as well. And x on x minus 1. Now, again, this one we've got a degree here that's 1 less. So if we graphed x times x squared minus 1, okay, or x times x plus 1 times x minus 1, we know that we've got asymptotes at 1 and minus 1. It crosses the x-axis at 0. So we're looking, if you drew that up and saw the signs, you're able to get the correct parts, correct signs of x over x squared minus 1. And then we were able to look at, okay, what happens as it approaches the asymptotes and as it approaches infinity. Now, can I just go back? I just want to go back to one graph that we looked at before. This one here, where we've got x squared plus x minus 2. Now, I said that one it doesn't go towards the origin. And that's because that is a greater degree than that one. Now, if we did the polynomial division there, and I'm not going to do the whole thing, but it's going to be x, probably plus or minus something. Not really worried what happened, but that would be a fraction. It would be on x minus 2. Now, again, as it tends to infinity, that part would tend to 0, which means the function would tend to x. So I think, I didn't say it before, I probably should have, that this function as it'll go off, will start to tend in each direction going through, and it's a little bit harder because the scale's really weird here, but it'll tend to go towards y is equal to x. So that would be, you'll get an oblique asymptote as such, because it'll go towards y is equal to x. So just take that into account as well, because if you do the division, as I said, if we do the division, that's going to be, that's because it's a greater degree of that one, it'll go in x times, x goes in x squared, x times, with some remainder, and that remainder will tend to 0 as x approaches infinity. But as x approaches infinity, that'll approach infinity itself at the same rate, which would be y is equal to x. So that wanted to come back to, just to show that's where we would have that idea after looking at what happens as things tend to infinity.